So we were talking about general dynamics, right? In the last class, we talked about how can we use Newton's second law to study the dynamics of a particle, of an object, which we're basically, generally we are studying rigid bodies, but in an idealization form, we're looking at that rigid body as just a particle. Later on during the semester, closer to the end of the semester, I believe last 2 weeks, we'll talk about rigid bodies and how can we actually use whatever we've learned to study the motion of a rigid body. There are some tricks there and the equations become obviously longer. But we talked about how to study dynamics of a particle using both Cartesian coordinate system or in Cartesian coordinate system and in normal tangent or tangential normal coordinate system, or any way you want to refer to it. Now, the last piece that you need to know, and it's going to be part of the exam, is how to study the dynamics or how to study dynamics of a particle in polar coordinates. Now, which one you choose is up to you, depending on the information given in the problem. Depending on which one is going to make your life easier, which part of it comes from experience solving problems and looking at a specific problem, should give you a hint depending on the way the motion is, the way the geometry of the problem is, the way the information is given. That's the part that comes to you based on experience, to be honest. The more problems you solve and the more problems you see, you have a better sense of which coordinate system is the best option for the problem you have at hand. Now, the last piece of this scenario is how to solve it in, as I said, polar coordinates. So I'm going to put it as, let me see if I remember which color they use. I think I was using black for numbering. So that would be polar coordinates. So we are doing the same thing, right? Free body diagram, kinetic diagram, looking at the components of acceleration on kinetic diagram, looking at the components of possible forces. We said we have like 5 possible forces when we're dealing with a particle. Those forces on free body diagram, and then write these the equations of motion using Newton's second law, right? That's pretty much the whole process. That's the whole process. Then, depending on what information are given, what we are asked to find, we just pretty much is just a math, playing around with geometry and math and trying to find the unknowns based on the information we have. Yeah. So just to a quick review before we look at examples in this one. We said, well, the polar coordinate system, if we have, let's say, XY, and let's assume that we have a path like this, and your point is here, your particle is here. Given that, if this is R, which basically the position, this is R, and this is the increasing theta, and assume that this is the origin. Your R theta or polar coordinates R would be, it points in the direction of the radial line from the origin to point P, right? So that would be your ER. I don't need that. This is ER. And this would be your E theta. Right, perpendicular to ER and points in the direction of increasing theta. So theta is increasing this way. We'll get E theta in this direction. Just as a recap, we talked about this coordinate system. Now, once you have this, well, you can find out your components of acceleration in polar coordinates. We talked about those in kinematics when we were talking about position, velocity, acceleration, and you can just write the Newton's second law, right? Summation of forces or is equal to mass multiplied by the acceleration. So I'll just write it here. The summation of forces as a vector is equal to ma as vector. Now, since you are in polar coordinate system, we can write it, we can decompose it in 2 equations, one along R, one along radial direction, one along theta direction, right? So we can just write it as summation of forces in r direction is equal to MAR, and summation of forces in theta direction is MA theta. And again, from kinematics, we already know that AR was R double dot, or second derivative of R with respect to time, minus R theta squared, or we can just write it as R double dot minus R omega squared, right? Theta dot being omega. Can look at it that way. And A theta, or acceleration in theta direction, we derived that to, I think it was 2R dot theta dot plus R theta double dot. Dot first derivative with respect to time, double dot second derivative with respect to time. So this we can actually write it as 2R dot omega plus R alpha. Theta being omega being angular velocity, alpha being angular acceleration. So this is just, these are not hopefully new, and you remember these from before. So everything you need, you already know, right? It's just the coordinate system has changed. You have to look at those forces. You have to find the components of those forces in r and theta direction. You have to find the component of accelerations, acceleration components, AR and A theta, right, in R and theta direction, and then just write the Newton's second law, right? Summation of forces equal to MA. Just as also last note, in circular motion, right, we had the special case, the same story like tangent normal, and also in this case we had AR was, well, R double dot. Well, if we, let me draw a circle here. Let's try to do. And if this is the radius R, and this is the origin, then you will get, let me use the same color. You will get ER and E theta. This being in R direction, this perpendicular in increasing theta, assuming that this is the increasing theta. So in circular motion or in circular path, R is constant. You can just represent that with lowercase r or uppercase r if it's you want to distinguish that from what we had before. But in this case, R is constant. So if you look at AR and A theta, R double dot becomes 0 wherever you have R double dot, because R doesn't change with respect to time. When you take derivative with respect to time, that becomes 0. So R dot and R double dot both becomes 0. So this becomes minus R omega squared, and A theta becomes just R alpha. All right, that's pretty much it. The theory part. Again, there's nothing new there, but you have to take a look at a couple of examples. We see how we draw the free body diagram. Make sure that the vectors for all the forces are correctly positioned. The angles we know, and we know how to decompose the vectors in correct directions. And kinematic diagram side, you just have to be able to calculate these two components for the acceleration. All right. Well, let's look at an example. I'm just going to stay here for a few seconds. So I'm taking notes. All right. So example. Let's say we have a slider. I think this is a good example. Let's say we have rotating a slider. A lot of the things that you see, you might think that where do they come from, and why do we even create such a weird systems that we try to study? But a lot of these actually are commonly used mechanisms in different engineering or mechanical or obviously machineries, right? If you zoom in, on a small portion of a big machinery doing some operation in manufacturing or assembly line. If you zoom in, these are small portions are part of the system. It's a small mechanism as the whole system. If you look at the whole system, is formed by a lot of these small mechanisms. So that's basically what we are doing. We are so focused on very simple, I would say relatively simple small mechanisms. Then if you have a more advanced course, you kind of start zooming out and you look at bigger pictures, that now what happens if you have multiple of these mechanisms, and how can you actually design a machine or design a specific mechanism that can do a specific motion for you, right? That's a totally different story. But just keep that in mind. These might seem trivial, but actually they are important because a lot of complicated motions are formed by these simple mechanisms. And that's why we want to be comfortable with studying these mechanisms, a lot of these at least. Some of them might be trivial, to be honest, just to test if you understand the concepts, but a good number of them are actually coming from more complicated systems, right? All right, so we have this, let's say, a rotating bar, and it's rotating in this direction. We call this theta, and we have, let me see the dimensions. Call this point O. We have this box, or whatever you want to call it, crate. Let's just go with a box on it. Call this box B, and this bar is bar OA. There is a friction here, mu. I can write it probably better, mu. This distance from point O to where this box is at this specific moment is 0.4 meters. You have a bunch of stuff here. Let me put it. You have, you know, the angular velocity theta dot, and you know the angular acceleration. I think theta dot is, and put here, theta dot is 5 radian per second, and theta double dot is 3 radian per second squared. Mu is 0.2, is mu k, and it's 0.2. We can add it here. This is mu k. I think that's pretty much it. And theta also at this given moment is, at this specific moment, is 40 degrees. Let's see if I can write it better, 40, so we can actually read it. So the problem statement goes as the 100 kilogram block B slides along the rotating bar AO. Right? We know mu k. I'm not going to write this. I gave you all the information. In this position, in this position, meaning at this given theta, and for that angular velocity and angular acceleration, find, determine R double dot. Right, it's pretty clear. Hopefully you know R, where, what is the, this is R, right, from point O to where your box is, your block is, and this bar is rotating. The slide or the block starts sliding down. You know the friction. it starts accelerating. You want to know what is the acceleration of the block on this slide, right, in R direction. So I can think about that as just a linear acceleration. If this bar was not rotating, and or better to say the motion of the block with respect to this bar. So forget about moving bar, rotating bar, and this block is sliding down. You want to know what is the acceleration in this direction. The acceleration, I can think about, if you want to be very technical, the acceleration of this block with respect to this bar. All right. So same story. Start with whatever you want to draw the free body diagram for. Draw the free body diagram for that. Make sure you know your coordinate system. The positive direction, represent that coordinate system on your diagram so you know where everything is. And look into acceleration components. Form the equations by writing Newton's second law. So that's what I'm going to do. I'm going to, in this case, I'm going to isolate this block. Right, I'm going to look at the free body diagram. Apparently, this is like the free body diagram for this. Right? Isolate. There is nothing else you can draw the free body diagram for, and that's why I went for the block. You have the most information regarding your block. You know its friction, the friction it has. You know how the bar is rotating. I know drawing the free body diagram for the bar doesn't really give you that much. You can try, but I don't think it goes anywhere. So let's draw the block. Right there is equal to, I'm going to draw 2 because I want 1 for free body diagram and I want for kinetic diagram. I want to show the inertial forces. So this would be my free body diagram. This would be my kinetic diagram. All right. So what forces? Oops. Tell me, let's start the free body diagram and tell me what forces, which direction I have to put there. While you're probably writing and you're going to tell me forces, I'm just going to put the coordinate system here. This is ER, clearly in R direction, right? Points in that direction. And since theta is increasing this way, this is E theta. This is my coordinate system. Friction going upwards on the beam, yes, on this rod. So I'm going to put the friction there. Going upward. All right. Actually, yeah, let's just put it upward. Because it's most probably slide. Actually, I don't know if it's going to slide down or slide up. So here is the thing. We are going to put it upward, but I'm not sure because I told you that it's going to slide down, but depending on how fast this rotates and what is the R component of acceleration, remember on this component, I'm going to put this there so it's easier to talk. So you're going to have 2 components of acceleration, right? One is going to be AR, and I'll say MAR, and one is going to be A theta, I call it MA theta. Now, depending on how big your AR is, right, there is a pretty good chance that it starts sliding up. Depends on what you get from the free body diagram on the left and whether the components of weight is going to overcome the friction or not. Right? So the direction of friction is not actually that clear. Right? We're just going to put one direction. We can just put it in this way, as someone said, I'll put it in that way. But keep in mind that it's not really clear because, as I said, that it's sliding down, but I'm going to correct myself because we don't know how much the component, how much is the acceleration in R direction. If it's pretty good amount of acceleration, it starts going up, right? So I'm just going to put it here as friction if I can find a way to actually give me a second, folks. All right, now it should work. So this is friction Fk. Put it this way. What else on my free body diagram? You have 5 possible forces, right? Just think about those 5. There is no cable here, so that's gone. Rope or string, so that you can forget. There are 4 left. So we have weight downward, exactly, mg. So I'll put it right here. This would be my weight, mg. What else? Took care of 2 out of 4. Normal force, and remember, normal force is always perpendicular to the surface that the object is in contact with, right? So that means this would be my normal force. I'll just call it N. All right, so that's all we needed. That's pretty much all the forces. Kinetic diagram is pretty straightforward. Multiply mass with the components of acceleration you have in that specific coordinate system. Now, could you solve this problem in tangent normal coordinate system? Most probably, yes. Give it a try. You can solve this in tangent normal coordinate system as well. I haven't done it. I think you need everything you have, but you have everything you need, but I have to double check. Let's form the equation. Summation of forces in r direction is MAR. Summation of forces in theta direction is MA theta. For now, just forget about MAR and MA theta. Let's just play around with what we have on the left side. I am going to make sure that you guys see the angle. This is theta. Don't want anyone to get lost there. So we have theta there. That theta is equal to, I don't want to mess with the drawing here, but if you look at this one, this theta is equal to this theta, or this angle is equal to this angle. I'll let you play around with triangles and figure that out the way you're comfortable with. Let me get rid of that. All right, so components of the force in r direction. What do we have there? How do you decompose the forces you have in r direction and whether they're going to be positive or negative? Fk, okay, Fk minus mg sine theta, which is 40, exactly. So mg sine 40, as Sama said, I'll just put it here, is equal to MAR. Just leave AR for now there. We'll deal with it later. How about theta direction? What are the forces, components of force in? All right, we get N minus, here's a consensus, at this between Sama and Connor, they both agree. N minus mg cosine 40 degrees, right, is equal to MA theta. That's pretty much it, all the forces, and then you have the components of acceleration. Let's look at those now separately. So AR is equal to well, in this case, R, I used uppercase R. So I say R double dot minus R theta dot squared. And I'll just leave it as is. I can get rid of that. And A theta, for acceleration in theta direction, you can write it as 2R dot theta dot minus or plus R theta double dot, right? That was plus R dot theta plus R theta double dot. Yes. So I plug everything into those two equations. Also, we know Fk is mu Kn. So I'll just replace that. I'll get mu Kn minus mg sine 40 degrees is equal to m r double dot minus r theta dot squared. And for the second one, we get n minus mg cosine 40 degrees is equal to m 2r dot theta dot plus r theta double dot. All right, see what we have and what we're missing. We know mu k, right, is 0.4, so that we know. N we don't know really. M I know is 100 kilograms. G is, well, acceleration due to gravity. Sine 40 we can calculate. M you know. R double dot, something we want to calculate, right? We're asked to find R double dot. R we know. Theta dot we also know, we're given. So first equation, N and R double dot are missing. Second equation, we don't know N. M we know, G we know, cosine 40 we can calculate, M we know, well, 2 we know. I don't think I needed an arrow there. R dot, do we actually know that? Yes, we know it and it's missing. So R dot, that was part of the problem. Meter per second. I have to be more close about the information. So R dot is given. I wish everything could be solved that easily, right? If unknown, just give you the value and put it there and problem solved. R dot we know, theta dot we know, right? R we know, theta double dot also we know is given. This is equation 2. So in equation 2, the only missing component or the only unknown is N. I can find N from there then. Right? So we can say from 2 N, let's move things around. M to R dot theta dot plus R theta double dot divided by, well, not divided by, actually, just add things up. Just move, goes to the other side, just add it up. So M 2R dot theta dot plus R theta double dot plus mg cosine 40 degrees. Right? So we know everything here. R dot is 1, theta dot is 5 radian per second. R dot is 1. This is 5 radian per second. R is 0.4. R theta double dot is 3. M we know is 100. Or G you already know. Cosine 40, you can just calculate N. From this one, you can get N. N will be, the number I got is 1.87 newtons. Use N, that's the problem. N and Newton, they look the same. I try to put the units up. So we got N. So now once we know N, we can go back to the first equation. Knowing N, you can actually find R double dot, right? You just move things around in this equation. The only unknown left here is R double dot. N, you know what the value for that is. So if you move things around, N becomes M R double dot plus mg sine 40 divided by mu k. So R double dot is, I'm going to go back and forth between these two pages. R double dot is mu k n minus mg sine 40. It's going to be mu k n minus mg sine 40 divided by m plus r theta dot squared plus r theta dot squared. You have everything again. This is mu k. It's given as, hopefully I gave you that, 0.2. And now you know 1.87. M you know, I'm not going to make it crowded here. M is 100. G, M again is 100. R is 0.4. Theta dot, I forgot, is 5. So we plug everything in and just do the math there. I don't have that number, to be honest with you. So I'll leave it right here for you to just, hopefully someone does the math or let me know. Becomes meter per second squared, right? So that's pretty much what we do, right? This it's embarrassing, I don't have the number. Should have calculated that. So once we know 3.7, I can just put 3.7. Should I just put SAMO here as a reference? So if something wrong, take the responsibility. Whatever that number is, we can just calculate that. So you get R double dot. All right. So again, procedure pretty straightforward, I think. Free body diagram, put the forces there. Put the components. The only thing that changed compared to Cartesian coordinates and tangent normal coordinate is that you're just putting different acceleration components for acceleration, right? In this new coordinate system, you have to remember, you know what the components of acceleration are, just plug them in and apply Newton's second law. The rest is just decomposing vectors in right directions and finding the, forming the equations, two equations that you get. Remember, you have to have enough number of unknowns. You have to have enough number of equations for number of unknowns. In this case, we had two unknowns, two equations. They're actually independent, these two equations. One of them just a function of one unknown, so it was relatively easy. Sometimes you have to solve them simultaneously. But we get R dot. Any question on this one? The process is straightforward. All right. If no question on this, let's do another example. Maybe sloping just to start below this. Then do good space management there. Let's just start from the next slide. A clean slate. So the next problem says we have a, let me try it here. We have I should never try this tool doing that. Let's see, what does it do? Not that impressive. Let me make it a little more. Let's do it this way. It's part of this trying to make that, but I think I'm going to end up explaining why it is. It's part of the of a circle, so that you can think about it as a big circle. We're just looking at part of it. We have a small sphere, or you can think about it as a cylinder, even in two-dimensional space. Oh, come on, that tool should work here. No, it doesn't. It's sitting there at the top of this. Think about it as a sphere sitting at the top of a semi-cylindrical surface. Right? It's a cylindrical surface there, and the radius for that is r. So I can just put it here. This is basically the center of this, and this is r. I know it doesn't do a good job representing that, but this is R. Radius R for this surface. Somewhere is in center, the center there. So this is the surface. Then we have a small sphere sitting there at the top. What we do is that we give it just a nudge, like a small hit. So that sphere starts rolling down, right? It starts going down on this surface. And this surface also is frictionless. So let's just forget about friction for this particular problem. It's not something that we want to focus on. So it's start rolling, right? It goes down this surface, and at some point, right, while it's rolling down, what should we call it? The sphere separates from the surface, right? It's going down. At some point, it just falls. Hopefully, the way I draw it makes sense, but it should have maybe made it more steep right here. Let's do it this way. This is part of a circle, and it gets separated. And let's say that's where it separates. It gets separated. So I'm going to draw it right there, assuming that it moved to this place. So it goes from here to here. It just starts from here. This is R also. Yep, let's put the path R. This is also R. Right. Hopefully the problem statement makes sense now. Let me just put a few words. So let's write it this way. A small sphere is at rest at the top of frictionless semi-cylindrical surface. It says the sphere is given say a slight nudge. I could write a better nudge, I guess. Actually, I'm not sure. We'll see. Nudge. Yes, as bad as the previous one. So so that it slides along the surface. The question is, find the angle theta, and here is from where it is to where it gets separated from the surface, and that angle is theta. Find the angle theta at which the sphere separates from, I guess it's the surface, from the surface. Oh my goodness. Surface. So free body diagram of that sphere, kinetic diagram of inertial forces, which basically are or acceleration components multiplied by the mass, and then write the equations. I will see where we go. Let's put it this way. At this point, I don't want to say no matter what the problem says. Obviously, it's important to look at the problem statement. But you kind of have a sense that that's pretty much how it goes, right? You find what you want to find. You find what you want to draw the free body diagram for. I'm going to isolate this. Put all the forces think about acceleration components, apply Newton's second law. So let's do it here. Let's use this tool used to be more smart, but apparently not. So I can try to draw it. So now it's working. So this, and then one for kinetic. Yeah, I guess when you're so off, it doesn't work. There you go. I'm gonna put the components. Remember, this is I'm gonna draw it where it gets separated, or close to where it gets separated. It's easier to visualize what happens there. It gives me at least a sense of angle. So I'm going to draw it as ER. This is along R, so it's ER. Now remember, perpendicular to ER, increasing theta. So that becomes E theta. ER, E theta, right? Left is free body diagram, right is kinetic diagram. So what forces do we have here on free body diagram? This is a sphere, obviously has some, can just put the mass as M, since it's not clearly specified. Should have said a sphere of mass M. So what forces? Well, out of those 5, again, no rope, string, or chain, so forget about that one. There are 4 left. Out of those 4, think about what we got here. While you're thinking on that, I'll put the components of kinetic diagram, because that's pretty straightforward. Just MAR, MA theta. Weight and normal force, exactly. That's pretty much all we got. So weight, downward, always. There's no argument in that. And this is, let's say, N. At the point of contact, perpendicular to the surface the object is in contact with, right? So if this is the surface at that specific point, perpendicular to that surface, gives me normal force. Normal force, and this is mg, right? That's pretty much it. So let's write the equations. Summation of forces in R is equal to MAR. Summation of forces in theta is equal to MA theta, right? So the angles, that's usually the part that things get lost. So if this is that, this one is theta. So in R direction, what we got there? Is Sama only one who is awake at this time of the day, or she only had more coffee? She had more coffee than others. I don't know. Or
It's
maybe
probably because I had 2 cups of coffee already.
there you go. All right. I had just one, and I'm feeling a little hyper already. Or maybe nobody's in the mood of dynamics at this time of the day and week 6 of the semester. Give me components in R direction, folks. N minus mg cosine theta, exactly. Connor, I guess, had at least one cup of coffee. Mg cosine theta, right, is equal to MAR. In theta direction, well, that's relatively easy. Mg sine theta is equal to MA theta. Guys, if you have problems with finding the components, please practice that. I'm just going with this assumption that you've seen this in statics enough that at this point you can easily find the components, right? If you look at this mg force, you have to find the components, right? One in this direction, one in this direction, that gives you mg cosine theta, and that gives you mg sine theta, right? In that right triangle there. Now AR and A theta, well, AR is R double dot minus R theta dot squared. Actually, let's just use the R that we're using here. So R double dot minus R theta dot squared. What is R double dot here? We're not given that much values, numbers. We're going to find it as like a parametric equation. Yes, right? Because it doesn't change. Exactly, guys. Thank you, Francesca. Correct. Two more people who are now awake, or they were awake, they were just quiet. So minus R theta dot squared. Keep it that way. Keep it there. Then we have A theta, right? Is 2R dot theta dot big, and it was R, I think, theta double dot, right? Now, same logic, R is not changing. Let me put this here. So this is 0, R is not changing, so this is 0. This becomes R theta double dot. So plug in everything together, put everything together, n minus mg cosine theta is equal to minus mr theta dot squared. If I'm doing it correctly, r theta dot squared, yes. And then let me know if you see a mistake. Mg sine theta is equal to ma theta. A theta is, so it becomes mr theta double dot. Now we got it. We got here so far. My question is, not that it matters. I guess. Oh, wait, what are we looking for? Fine angle theta. Okay, yeah, I got lost at some point. What is the what happens? Actually, there are multiple ways of doing it. But what happens? Just want to get the right equation. What happens when it separates from the surface? Right, so we draw the free body diagram here, and kinetic diagram, everything was good. Now, no normal force, exactly correct. So no normal force, once it gets separated, once separated and becomes 0, right? There is no contact between the surface and the sphere. So you can get either from 1 or 2. I wanted to go for 2 because I want to get theta dot. So you will get from the first one, let me write it here. From the first one, you will get g cosine theta is equal to r theta dot, right? And from there, you can actually find theta. So you can think about this as cosine theta as r theta dot over g. So theta becomes cosine inverse r theta dot over g. You could go with the first equation as well. I just wanted to emphasize that n is equal to 0 when it gets separated. From the second, because we are not given enough information, either works. From the second one, we could get theta sine inverse r theta double dot over g. And depending on your, theta dot or theta double dot, you can just calculate theta, the angle. Right? So it really, all it matters is that I wanted to show you how to write the equations and what happens when it gets separated. All right. That's what matters. The rest is just depending on what numbers you're given, you just plug in and find the value. Whether you're given the angular velocity or angular acceleration, you can just use that and find the angle theta. All right. Questions, right, on this? Hopefully that was pretty straightforward.
So would that be our final answer?
Oh yeah, pretty much the final answer. Depending on what you were given, you could continue this. If you were given theta dot or theta double dot, that is theta squared, exactly. Thank you, Adam. This should be squared, and this is squared, this is squared. Of course, I missed something. All right. Hopefully that's great. So now I want to do a little, an example is a little more tricky, I would say, compared to these. These are like straightforward, right? The equations, Newton's second law, get everything together, and pretty much you can find your unknown. Now this one, the next one I want to talk about is you need to use a little bit of kinematics as well while you're solving the problem. Well, just let's go over this one and see how things work. The one that and we'll just walk through the steps. All right. So no question on this one, right? Hopefully straightforward. Right. Just make sure you get the direction of r and theta right, always. That's pretty much that point, and the part that you have to find the angle and decompose the vectors. I think those are the parts that most mistakes happen. So I'm telling you now that just be a little mindful when you're going through the steps. Once you get everything right on your diagrams and directions and angles, rest should be relatively straightforward. All right. Another example. Now in this example, we have the diagram is relatively easy to shape, so just draw it here. This is just some ceiling. You have mass M kind of ball that you let it go. It's swinging downward, and then that's basically where we are and we want to study. So it was, it's here now. Let's see if I need to give you more information. This is right there, and then you have your mass M there. There you go. And this length is L. This length is L. This angle, this is where it was released from theta. Right, so problem statement that goes as the 2 kilogram mass is released from rest with the string with the string horizontal. That's trying to say that's where we were at the beginning, with the string in horizontal position, I guess. It's the best way I can describe it. The length of the string is L equal to 0.6 meters using some extra Newton's second law. You're usually not told this, but this problem is being nice and trying to give you some hints. Using Newton's second law, in polar coordinates, we can definitely solve this in tangent normal coordinate system as well. Coordinates, find the magnitude of velocity of the mass and the tension in the string when theta is equal to 45 degrees. Usually 45 degrees is nice because even if you make mistake with sine and cosine, it has equal sine and cosine, so you still get the right value. Should remember not to give you 45. All right. Isolate this. Pretty much it's mentioned the problem that what is expected from you. Right? Newton's second law and polar coordinates. So you have to draw the free body diagram. Really, there is nothing else in this problem that you can think about of drawing free body diagram for. The only thing is that just mass m released, and you know the value for that mass, so you have the most information about it, I would say. Unless you think about that string, but you can't really draw a free body diagram. You can, but nothing comes out of that. So drawing the free body diagram and kinetic diagram, let's just start from there and see where does that take us. This one, and then this one. And let me put the coordinates there, ER along the R, or in this case L. Remember, you can think about this, but I'm putting my XY coordinate here, kind of, if you want to think about that. So this becomes ER. Doesn't really need to know where XY is. ER points in a radial direction, right, from the origin, somewhere that you're thinking the origin would be, which obviously this is the best place for the origin. Right? Obviously, naturally, you take this origin. And E theta in the perpendicular direction, increasing theta, so E theta. So that becomes ER. This becomes E theta. All right, so free body diagram, what are the forces there? Straightforward, right? Out of those 5 forces, tell me what we have here. Number 5 forces. Force in a string or cable. Hopefully I remember what to see. Weight, normal force, friction, spring. Right? There is no spring. Out of those 4, tell me what we got here. I have the weight and tension, exactly. 45 degrees upward, exactly. So I'll put it here, 45 degrees upward this way, tension, and we have the weight downward. That's T. That's mg. On the kinetic diagram side, well, let's just do whatever we always do, pretty much just put the components there, then we'll calculate ma theta, and this is mar. And let's take this, so this angle, remember now this becomes theta. Let me make it smaller, probably. There you go, now it's good. So let's write the Newton's second law and see what we get out of that. Summation of forces in R direction is MAR. Summation of forces in theta direction is MA theta. In R direction, what do we have in R direction? For the ones who are lost with angles, again, I told you the most possible place, the most mistakes happen are angles. So this becomes theta. So that might help you. So what components do I have in R direction, positive and negative? What are the signs? Basically, I'm looking at the free body diagram side, right? This is your free body diagram. This is your kinetic diagram. T minus mg, almost there, right? T minus mg sine theta. This becomes your mg sine theta, and this becomes your mg cosine theta, looking at that right triangle, knowing the angle theta there. So that becomes T minus mg sine theta, right, in R direction. Let's just put MAR. I'll just separating the steps so it's easier for you guys to follow. In theta direction, well, we get mg cosine theta is positive on free body diagram. On kinetic diagram, MA theta. Mg sine, what did I do? Yes, thank you, Richard. Should be the other way around. Mg sine theta minus T. Yes, mg sine theta is positive. Mg sine theta minus T. Yeah, T is negative. All right, so we know AR and A theta, and think this is the motion it goes to, right? This is where this mass started. When it's swinging, it goes through this path, if you want to think about that. It goes all the way to the other side, comes back, and it starts swinging. And you look at the other stuff about this swinging at some point in vibration. So for now, just let's look at the path, right? So it's going on this path. And this is a kind of, okay, let me just write it and figure it out together. So it's R double dot minus R theta dot squared. That's what we had for that. What is R double dot here? Zero, exactly. Thank you. So it's zero, right? Because R is L in this case. The length of the string is constant. It's just swinging. So that we don't really have any change in the length of the string or in R direction where the particle is. The particle doesn't really move in R direction. It only moves in theta direction. So that is zero. Since it's fixed, this becomes R minus R theta dot squared. And then you have A theta that was, I forgot what, so it was 2 R dot theta dot was, I think, R theta double dot. Following the same logic, R dot is 0. So this is 0. You'll get R, let me just replace it. So we get L theta double dot, R is L, right? So let me just replace it. And I'm going to replace it for that one too. Just right here, minus L theta dot. So plugging in the values, you get mg sine theta minus T is equal to minus ml theta dot squared, and you get mg cosine theta is equal to m l theta double dot, right? All right, so from the first one, I can actually write the equation for T. If I just move things around, this would be m, let's factor it out, would be g sine theta plus L theta dot squared, right? That would be equation for T. I know M, I know L, I don't know theta. I remember theta is, if it makes you have a better visual sense of that, theta is basically just omega, right? This is just omega. You can think about that. If you were telling me this is a motion on a circular path, and you were saying, well, this is basically minus r omega squared, and that one is r alpha, I would have accepted that. Yes, it's basically a circular motion. But just make sure that when you make the assumption about this motion on a circular path, it is actually a circular path. In this case, it is, right? R is fixed. Sometimes the path is actually not a circular path. You have to be mindful of that, and we have to pay attention to that. All right, so let's just wrap this up. Now, we don't know omega, right? That's the problem right there. So we don't know t, and we don't know theta dot or omega. From the second one, right, we don't know theta double dot. T is not there, and theta dot also is not there. So we don't really get anything out of that we can use to solve for theta dot. Right? You can write theta dot as this, or you can write it as alpha if you want to think about it as alpha. I'll write it as alpha. I think for the point I want to make later, it's easier for you to see it as alpha. It's pretty much the same thing, angular acceleration. Is equal to mg cosine theta divided by ml. And I could get rid of m, and I just write it as g cosine theta over L. Now here we are. We know theta dot, theta double dot, as a function of theta. We need to find, so remember what the problem is. The problem is we have to find the magnitude of velocity of the mass and tension in the string. Both of them are unknown in the first equation. And the second equation doesn't give us that much. Second equation doesn't give us neither omega or theta dot nor t. So the second, what do we do here? We need to know either theta dot or t to be able to solve the first equation, to be able to solve this for the other one. Right? Both unknowns in this equation are what the problem is asking for. And the second equation also is not giving me that much. So what do I do? How can I find t and theta dot, which is the magnitude of velocity? How can I find that with what I'm given? Here's the trick. Go back to kinematics, right? So I'll put it here for a reminder. Remember, for a motion on a circular path, we had omega d omega is equal to alpha d theta. We had this relationship. And that's what I'm going to use here. Right? I'm going to say omega d omega is equal to alpha d theta. Now, I know what alpha is. Alpha is a function of theta right there. This is alpha. I know the range for omega. Omega, what is the range for omega? I don't know the final angular velocity. What is the initial angular velocity? It's 0, right? It says it's released from rest. Exactly. So that's 0. Theta, I know that one too. It starts from 0, and I'm told that we want to know these parameters at theta equals to 45 degrees. So 45 degrees. I'm told that it starts from horizontal direction, goes in this direction, theta, and up to 45 degrees. So from here, actually, you can find, so this one gives you, let me just write it again. Omega final, omega d omega is equal to 0 to 45 degrees, g over L cosine theta d theta. Well, that's an easy integral. G over L comes out as constant. Integral of cosine theta, it becomes sine theta. And from the left side, you will get 1 over 2 omega squared from 0 to omega f, final, whatever the value that you want to find. And from the right side, you get g over L sine theta from 0 to 45 degrees. Right. That you can just get omega f. So that gives you omega f is equal to square root of g sine 2g sine, it becomes 2g sine theta over L. And you know everything here. You know what G is. G theta is 45 degrees, so you just plug that in. I could actually write it as, since I'm plugging in everything, let me just write as sine 45 degrees instead of keeping it as a parameter. That's more appropriate. So this is sine 45 degrees. Plug in the values. G sine 45, L is also given 0.6 meters here. So you plug in the values, you'll get final angular velocity as 4.8 rad per second. So now this is your theta dot. All right, this is your omega or theta dot at theta equals to 45 degrees. So now you can go back to the equation right there, to this equation. I'll call it equation star. Right? And now you know omega or theta dot, you know L, you know G, sine theta, everything in that equation you know. You can just find T. Right? So I'll just put T is equal to, or let me just put it as from. So now from star, you get T as, I'll just give you the final value, and obviously always double check my number, newtons. There you go. So you got your velocity and you got your tension. All right. This was a little trickier. We wrote the equations, but then we ended up in a situation that we have unknowns, right? We have two unknowns. The first equation, those are the unknowns we want to find. But the second equation doesn't really give us that much. So we had to go back to what we know from kinematics. Remember, this was omega d, omega is equal to alpha d theta. And in the linear motion, we had it as v dv is equal to a ds. So it's the same equation, just in angular direction, in angular or in rotational motion. So we used that to find one of the parameters that we were looking for in the first equation. And then from there, we could find the tension in the string. All right. Question on this one. Time is up. So